Wow.
You want the earphones to check if it's working or not.
So those of you on the live stream, we're just going to give it a couple more minutes until people join. Thanks a lot.
I always intend to bring this.
I get really got a ham on that. Whoa.
Is the microphone working? Cool.
Yeah.
Feel free to pull out some of those chairs.
Oh yeah. I thought you were going to say the bread. No, I had one of these, and I don't know. That's probably just like my use this not.
So, Ollie, shall we start? Or
Yeah, I think we can.
all right.
What we'll do when people ask questions, you will take questions.
Yep, I will. In case, remember, remind me.
Hold on a second. Okay, let's go.
All right, so welcome to this Java community talk. I'm Paolo Ambrosio. I'm principal engineer in Sky Identity. And this presentation is primarily about the Java web stack, but what I say can be applied to any language or framework. So we'll talk about the threading model of web applications and in the specific why a non-blocking asynchronous model should be preferred. I'm going to start by setting the context first. So this naive abstraction of what a web application is probably how less experienced developers see their web application, especially if they haven't been exposed to service-oriented architectures in production. We have incoming requests, outgoing requests, the controllers and service layer, plus database queries. But in the modern enterprise world, this is far from being a decent approximation. In reality, is more something like this. So nowadays it's quite likely that your system sits between other systems and affects and is affected by any kind of failure, especially input-output calls. To make it even more complicated, the software is just the inner layer of many other. There is the hardware at the bottom. There is probably a virtualization layer, operating system, maybe containers, and eventually we get to the web server and the application. This presentation will look at what's in green there. That are the two inner layers that we're in control of. But before we dive into it, I'll introduce some concepts that are going to be used throughout this presentation. The difference between synchronous and asynchronous. For short, when a synchronous method is called, the caller needs to wait for the response. When an asynchronous method is called instead, it's usually the method returns either a future, or there are other ways of signaling the success or failure of the call, with either a callback that's passed as a parameter or with message passing. In difference between blocking and unblocking, so when a blocking method is called, the current thread cannot be interrupted by other threads. We'll see in the next slide what that means. And there are all kinds of permutation of synchronous blocking, synchronous non-blocking, etc. So, for example, synchronous blocking is the traditional web application where we have synchronous controllers making blocking I/O operations, or for example, synchronous non-blocking could be a CPU-intensive task where the application loops and checks for if the thread should be terminated or not. I can show, for example, well, I'll wait till the next slide to show an example of blocking threads. So, what means for a thread to be interruptible? If one thread wants to stop another thread execution, it can call its interrupt method. But the interrupt method only works if that thread is doing either an operation that can be blocked, or otherwise it's gonna just set a field in the thread, and that field can be queried by code. So we can see from if I can get out of this presentation, yeah. We can see on Oracle pages 2 example of is not this one. Which one? It's an empty. So on the slides, or so has it picked it up? All right. So we can see here the first example is a for loop where the thread calls the sleep. Sleep is can be blocked, and if it's blocked, if the thread is blocked, it throws an interrupted exception that can be handled. Second example is, in this case, a CPU-intensive task that's split into batches, and after each batch, the thread checks if it's interrupted and can return immediately. So we'll go back to the slides now. So this means that in a thread that is not in an interruptible part of its execution might never terminate, or might terminate well after the request is issued. So we'll see now. Enough for the boring introduction. So we'll talk about the threading model in the web servers. So modern web servers usually offer two kind of I/O modes, blocking and non-blocking. Tomcat 8 and Jetty 9 offer the non-blocking as as default, but and sometimes even the only option. It's important to understand because it's not what it means, because it's not going to make the application magically non-blocking and asynchronous. It's not going to solve the typical implementation. Highlighted is income the threads the only one thread that loops into accept call to accept the incoming connections. Then all those connections are passed to the worker threads. It is always blocking on the system accept call, but this is usually not a problem because even if it's blocked, it doesn't need to do anything apart from accepting other calls, and it doesn't handle HTTP requests, even if the HTTP requests come on top of the TCP layer. So what happens in the blocking implementation is that whenever a connection is a connection received is passed down to a worker thread, and that worker handles the connection for its entirety, even if multiple HTTP calls are issued on that same connection. This might not look like a big problem, but HTTP 1.1 introduced keep alives, and so it can be that that thread is waiting for another HTTP call and blocked just because it's been assigned a connection. So it can be blocked for several seconds, and the number of worker threads in the blocking IO implementation limits the number of concurrent connections the system can handle. For this reason, sometimes the old way of doing it, of getting rid of this problem, is to put Apache HTTPD or Nginx in front of it. These are usually more scalable and pass and create a single connection to the Java web server for each HTTP request and handle the TCP keep alive at their level. This is the common configuration is to send is the reverse proxy configuration, where there is one connection issued by Apache or Nginx to, for example, Tomcat for each HTTP request. This comes with problems because whenever closed, it stays in time wait state for about 2 minutes, from spec, and so it's quite clear that it creates 120 times the RPS, the request per second, that the system is seeing constantly. So if we look at the non-blocking IO implementation instead, this introduces another thread pool called Selective Threads, and this is between the acceptor threads and the worker. Each TCP connection is assigned to a selector thread, usually in a round-robin fashion, and the purpose of this is to listen for incoming HTTP requests on the TCP connection that's been assigned to, and pass them to the worker pool. This has the benefit of decoupling the worker thread pool size with the number of concurrent connections that the server can handle, but not number of HTTP requests that the server can handle. Because the HTTP requests are passed down to the worker threads, and so we'll see that blocking controller imposes the same limit on the number of concurrent requests that the server can address at any point, even on with this non-blocking implementation of the web server. So really switching from a blocking to non-blocking servers is just configuration. So there is no reason not to enable it in modern web servers. Let's talk now about outgoing connections. That's the main source of problems in our web applications. And and let's see how the same configuration apply to them as well. We will have to consider how threads work and how they can block how they can block and impact the stability of the system. So let's start again with a blocking HTTP client. These are three phases. First, let's assume that it uses a connection pool. That's the most common scenario. There are the connection. The client requests a connection, establishes the TCP connection, maybe if not kept, if it hasn't been kept alive, and then the request response phase starts. There are several timeouts that can be set up, and the connection request timeout is also interruptible, so the thread can be interrupted before the timeout happens. But in the other two cases, the established TCP connection and request response, the thread is not interruptible, so we need to wait for the timeout. Even if the connection timeout is connection timeout is the timeout for establishing the TCP connection, but in the blocking I/O, the request response doesn't really have its own timeout, because the socket timeout applies only to data packets received. So in read, so the idle time between subsequent data packets. So it can be that we receive one data packet with the parser response, and so we don't time out in what we expect the timeout to be. Also, write is not including this timeout. So let's say we have, and usually this the way to be unblocked is only the system is unblocked only when the operating system closes the socket. So what can happen, for example, if it happened in production where a firewall was silently dropping all connections after a certain idle time, those connections would be seen from the operating system perspective as established. So Java would try and use those sockets. The operating system would consider them alive, would try and send the packets. The firewall would drop them without sending either reset or initiating the handshake to close the connection. So operating system would retry sending those packets, doubling the time waiting between resending the packets. At some point, usually after 16 times and doubling the time every time, that's about 15 minutes, the connection would be dropped and the thread would be unblocked. So we can see easily how this can be a problem. If all connections start being dropped by the firewall, in the blocking I/O model, the system would be blocked for about 15 minutes. So how can we solve this? If we introduce a thread pool executor, for example, what Hystrix does, we can decouple the application threads being blocked with, so we can keep the application threads in an interruptible state, even if the executor thread that is doing the actual I/O operation becomes blocked. This history is widely used in Sky, and it adds other functionality as secret breakers, caching, and fallback on top of it. So it's a quite an easy fix. We can see the sequence diagram here. What happens when the I/O operation is blocked and cannot be interrupted? The server is able to release to decouple the worker threads and release them from processing the request, but the executor threads would still be blocked. This means that the pool would start filling up, and eventually the executor thread pool wouldn't have any available threads and would start failing. This gives us deterministic timeouts, even if it would start failing after a certain point. So In this case, the only real option to keep the system stable is to use a non-blocking client or using a thread pool in between. If you use the non-blocking client, all your operations are interruptible. Change the application to use a non-blocking client is also quite easy. We can even block the calling thread by calling, for example, the .get on the future, and that would decouple, even if it's not a very good solution, as we'll see in a minute. This is better than using a brand. So finally, we'll and this between the two components, the server part and the outgoing operations we just talked about. The classic blocking controllers, for example, Spring Boot or JAX-RX, etc., limit the concurrent requests that can be processed at any time because they associate one thread per request. So in this case, fast responses are fundamental for the stability of the system. We see that instead, with the asynchronous model, we decouple response times from number of concurrent requests that can be served. In this diagram, we see the two differences between blocking controllers that where the threads, the worker threads, are the worker threads that are assigned to process the request in the controller are blocked for the entirety of the operation, even if we use a non-blocking I/O HTTP client. And so instead, in the non-blocking controllers, the threads are free to process other requests, because we see in this part the thread is able to process other requests. So the downside, so we could, of course, the best option is to use asynchronous controller, non-blocking, but the downside is that requires a paradigm shift and a good framework support to make the code readable. So from what we've seen, non-blocking operations make our system more resilient. So, but migrating an old application to use the new paradigm is quite a challenge, especially for the controller and service layer. So we've seen also what each layer adds to the resilience of the system, and we'll see. We saw that unless we go non-blocking asynchronous on the whole stack, we still hit problems, and we can't expect just by magic to introduce non-blocking I/O without any fundamental code changes. So I've prepared demo application to show the difference between asynchronous non-blocking and synchronous blocking, and this is the architecture of the demo. We see that the synchronous blocking controller calls the synchronous blocking service layer, and the asynchronous non-blocking controller calls the asynchronous service layer. And this is, I've used Drop Wizard. This might sound a bit odd for an asynchronous non-blocking model, but I just wanted to show that it's not really the framework that's important. So Ratpack or HTTP, for example, in this demo would almost only offer a syntactic sugar and better syntax. So what's important is the paradigm shift. So let's see. Sorry, not Q&A yet, but I've lost the pointer. So all right. So we also have we're going to exercise this system using Gatling as load simulator, and we'll have an HTTP dependency that we're going to control with YMOC to simulate delays. The parameters with I've configured have been quite low, so we'll have 4 worker threads in the application, and double the worker threads on double the virtual users on the load simulator. This reflects quite well the even if those numbers are very low. So in a real application, you would probably have 150, 200 worker threads. It reflects quite well the fact that there are usually many more clients than worker threads available. And about the request timeouts, I've set up in Gatling request timeout to be 3 seconds, as well as a socket timeout. And in the backend dependency, the client is configured for 2 seconds. I haven't considered the connection timeout, because in local it wouldn't. I don't want to go there and impact that. So 100 milliseconds should be plenty in local, but of course in a production system you should try and find what's the right amount connection timeout for that. Because for example from AWS it might take much longer. So it's usually best practice to test the quality of the connection first. And for the number of connections in the pool, I put it far above the number of threads, not to impact it, and the same in YMOC server. So let's see. Yeah, this is can be seen in on Hangout. Is it the code on Hangout? No. So I'm gonna try and do whatever I did before. Right. Yeah, I don't know how. Let's try the presentation mode. Yeah, is that cool? Yeah, so this is the Gatling simulation. Instead that we're gonna run 8 users over 5 seconds, and then keep them steady for 140 seconds. They're gonna call. They're gonna be in the loop, calling. In this case, it's a synchronous endpoint, and checking that it returns 200, or the asynchronous in the other simulation. If it's got a pace of 1 second, that means that if the request is going to try and make 1 request per second, but if it's so, for example, if the method call returns in, if the endpoint returns in 100 milliseconds, it's gonna sleep for 900 milliseconds. If it returns in above 1 second, it's going to do it straight away. Let's see, presentation mode. So I don't know how it's probably not readable. This
Did you say
Command plus. Yeah, that's better. All right. Right. So here we have in the top terminal we have the Vagrant box where I can control the responses, the delay for YMOC. I'm gonna run the application in local, and later I'm gonna start the synchronous simulation, and we'll see what are the response times from the application perspective. And I'm also going to introduce delays. So after 10 seconds, I'm gonna start a quarter of a second delay. Then after another 30 seconds, half a second, after 30 seconds, 1 second, and then eventually 1.5 seconds. So we can see now that the application is starting responding first in a few milliseconds, then roughly quarter of a second, etc. This is what the application thinks it's replying to, but in reality, this is what Gatling sees. So Gatling sees whenever it starts going above a quarter of a second, we see that the response time starts increasing above 250. This is why. Why is this? Because the threads, as there are 8 virtual users trying to get access to 4 worker threads, it's quite likely that the 5th request is going to be queued up, waiting for the thread to be available. This gets even worse when we go to half a second, because it's more likely that this situation happens. And by the time we get to 1 second, in this steep ramp up, the 4 threads, as Gatling is going to try and do 1 request per second, they will all align very quickly to a 2-second response time, because every time all 4 requests for 4 virtual users will have to wait for another 4 requests from the previous one that are going to take 2 seconds, and so every second there's going to be a sort of worst case scenario of all requests taking 2 seconds. Once we get to 1.5 seconds, we see that errors are returned, because the same thing works for 3 seconds, because Gatling is going to try and do at least 1 request per second. In this case, 1.5 seconds. And we see that there are more errors than others, because they're going to go above the 3-second request time that Gatling is expecting. So if we instead run the same simulation, but using the asynchronous endpoint, the asynchronous endpoint, and we start again the simulation, the delays. Yeah, in this case, I'm showing the graphs that are already taken from another run of Gatling, but they are the same. So in this case, we see the same application behavior. Nothing changes from the application perspective, but what changes is the Gatling graph from as seen from the client. In this case, everything is very similar to what the application returns. So this is because the 4 worker threads are not busy and are not blocking the HTTP requests, but are able to process the other requests in parallel, as long as they are free to accept the response from the downstream system. So all right, so I think this is everything I wanted to show. So why is blocking IO so popular if it doesn't have any advantage? Because of limited language support. So yeah, Scala has a very good way of dealing with asynchronous IO, asynchronous computation in general. Java 8 has introduced it and is going in that direction. Framework support is quite poor. For example, there are ArchiCTP, Ratbag that are have reduced it quite well, but the Spring Boot deferred result is not really, or JAX-RS with the asynchronous response. That's what I used in the demo. Don't offer a really good readability. So in Spring is as part of Spring Reactive is trying to fill the gap. by introducing controllers that return futures. That's so. Given Sky's resiliency capacity targets, I'm really surprised that hasn't been a big push towards asynchronous unblocking, because we've seen it in MPIs in the past. This is one of the major issue we face as in production. If there is one system slowing down, the other systems follow. So to end this, if you found these topics interesting, and or if you're already adopting asynchronous non-blocking model in your software, feel free to join the reactive Slack channel that I put in this slide. And there's probably going to be many more topics of interest. Asynchronous blocking just necessary for reactive, but there's much more than that. And now, if you have any questions,
Can you show the implementation of the controllers, the sync and async?
yes. So let's see. Yeah, I thought so. Damn Hangout. So he's asking not here yet. Oh. I don't know how to. Maybe if I go to presentation mode. Good. All right. So the question was to see the implementation of the demo application. So the sample resource. This is the controller. It uses synchronous service, and we should be quite familiar with this syntax, with the sync service being called and returning a string. The string return is OK, or a failure. And then the asynchronous, the quite horrible JAX-RS syntax. I just wanted to use the only standard I know to do this, but other frameworks will provide better syntax. In this case, the asynchronous service calls, and the call to the synchronous service returns a future, a listenable future, if I remember correctly, and this when complete does is basically a way of the async response is a callback object. So we complete with either an error or with the OK result. If you go to the service, the synchronous service is using the Apache HTTP client, the synchronous one. This is all the configuration that you use. In Dropwizard, you can use you can configure it just automatically, but I just kept it to be sure that I was configured the right thing. It actually Dropwizard does that. But I wanted to show all the options if you don't use Dropwizard, and it just executes the call and returns it passes the content and returns the string if the string is OK. The controller returns sync or async. The dependency returns OK or not. And the asynchronous one, if I can, the async service. Again, this is the configuration part. Uses the asynchronous HTTP client, the old Ning client, and it uses the execute method accepts a completion handler. Again, sort of callbacks, and on completed. So this means whenever the request, the response is returned, it becomes part. This method is called, and we can read the body, check if it contains OK, and return a future. Because in this case, I decided to return a completable future to the controller. and the completable feature is completed with async as a response. Otherwise, we complete the feature with an exception. So in this case, call returns immediately, but returns a feature that is that eventually will be completed. The better way of doing it would be to use like a reactive, like a RX Java or something like that, because that offers a much better syntax. But I wanted to keep it simple in this case to show that even with Java and traditional standards, you can achieve the same thing. Probably you want to use something like a Spring Reactive, Ratpack, or Rack HTTP in real scenarios, but to keep it more readable. But nothing prevents you from going asynchronous on blocking, even with traditional technologies. Yep.
I've seen that in both services. You configure the async client with those 3 different timeouts. Do they correspond to the different timeouts that you were saying before?
Yes, the only one is the request timeout that is only available in the asynchronous one, because it doesn't have a thread that can be blocked. The synchronous just makes a blocking call, so it can't be unblocked. So it doesn't have that setting. Even the client doesn't have that setting. The asynchronous only adds that setting the same as, and I've configured it to be. Sorry, I forgot to answer, to repeat the question, but it was about the timeout settings between synchronous and asynchronous. So the asynchronous adds it puts the request timeout to be the same as the socket timeout, and that's it. The rest should be exactly the same. I kept the number of channels the same, so 20 in the asynchronous, and the number of connections in the synchronous client 20 as well. One of the problems I had was with WireMock, that it says that the number of worker thread is 200 by default, and instead it is 10. So that's why I spent a few hours trying to understand why my application was misbehaving, and it was the dependency. So, any other question? Yes?
We were to book the report once and possibly from message.
So what's the message from the talk is that we should try and move from blocking synchronous web application into to non-blocking asynchronous, but sometimes it's very, very hard. We definitely need a push from to allow that to happen, especially for controllers. But if developers at least manage to get the web server and the service layer non-blocking, that would help enormously. Because the controller part, that's a totally different kind of fish. So it's probably much more difficult in existing applications to move to that model. And for new applications, I would say try and choose frameworks that allow to write readable code with asynchronous non-blocking from the start, instead of using old frameworks. Any question? Nope. So thank you.